Okay, so picture this. A computer that learns a new skill, but not because someone programmed it. No, this computer evolved, like a living thing. Today we're diving into the absolutely wild story of a computer chip that literally evolved its own solution to what seemed like an impossible problem.
So that's the big question, right? How do you actually teach a chunk of silicon a new trick when there's no programmer to write the code? I know, it sounds like something straight out of science fiction, but this was a real experiment. And the result? It's genuinely mind-bending.
All right, first, let's set the stage here. The researchers, they didn't just lob an easy problem at this thing. Oh no, they gave the chip a task that, given the constraints, a lot of experts thought was flat out impossible.
Now, on the surface, the goal sounds super simple. All the chip had to do was tell the difference between two sounds, a low-pitched 1 kHz tone and a much higher-pitched 10 kHz tone. You know, if it hears the low tone, it should output a steady high voltage. If it hears the high tone, a steady low voltage. Seems easy enough, right?
Well, not so fast. Because here's the catch, the big twist. The researchers took away the chip's clock. Now, a clock signal in a circuit it's like its heartbeat. It's the fundamental tick-tock that lets it measure time. So without that clock, the chip has absolutely no way to tell how fast or slow a signal is. It's like asking you to tell the difference between a 1-second beep and a 10-second beep, but you're not allowed to have a watch. That was the impossible challenge they set up.
So the normal way of doing things was completely off the table. And that forced the researchers to try something radical. They thought, what if instead of us designing a solution, we just let a solution find itself? And they were going to do it through a kind of high-speed digital Darwinism.
And the playground for this crazy experiment? It was something called a Field Programmable Gate Array, or an FPGA. The easiest way to think about an FPGA is not as a normal fixed chip, but more like a sea of digital Lego blocks. In this case, a 10 by 10 grid of them. You can change how every single block is connected and what it does instantly, just by feeding it a new design.
And the method they used to arrange all those little Lego blocks? A genetic algorithm. This is basically Darwin's theory of evolution, but for computer circuits. The idea is you create a whole bunch of random designs, you test them to see which ones are any good, and then you let the best ones breed to create the next generation. It is, and I mean this literally, survival of the fittest, but happening inside a piece of silicon.
Okay, so here's how that whole evolutionary loop actually worked step by step. First, they'd create a population of 50 totally random circuit designs, just digital gibberish. Step 2, they'd load each one onto the real chip and test how well it did the job. Then they'd pick the single best one, the champion of that generation. For step 4, they'd take that champion and breed it to create 49 new offspring, each one a slightly mutated copy of the parent. And then step 5, they just hit repeat. And they did this for thousands and thousands of generations.
And you know, this is where things get really, really cool. Because this wasn't just some computer simulation. No, they were testing these circuits on a real piece of hardware, which meant they could hook up an oscilloscope and literally watch a circuit evolve right before their eyes in real time.
So, at the very beginning, Generation 0, it was pure chaos. The circuits were just a random jumble of connections. The best one they found? It just output a flat line. It did absolutely nothing. As the researchers themselves said, none of the first circuits showed any ability to do the task whatsoever.
But, you know, evolution is patient. And after about 650 generations, something started to happen. You can see it right on the oscilloscope. This is the very first hint of a solution. See how the output for the low tone is kind of starting to stay high? And for the high tone, it's doing, well, something else. It's not a perfect solution by any means, but it's a start. The chip was actually learning.
Okay, now fast forward to generation 2550, and this is where things get properly weird. The circuit's getting way better at telling the tones apart, but just look at those waveforms. Those are not the clean, crisp ones and zeros of a digital circuit. They are messy, they're chaotic, they're analog. It's this incredible moment where you realize, wow, evolution does not care about our neat and tidy design rules. It's tapping into the deep, messy physics of the silicon itself.
In fact, the researchers who ran the experiment, they described these in-between solutions as, and this is a direct quote, utterly absurd to a digital designer. I mean, any human engineer looking at those signals would just assume the chip was broken. But to the evolutionary algorithm, this was just a necessary, bizarre-looking step on the path to a real solution.
And then, It's almost like magic. By generation 3500, this emerges from all that chaos. Look at it, a perfect result. A clean, steady high voltage for the one tone and a clean, steady low voltage for the other. Evolution had done it. It had found a near-perfect solution.
By the time it hit generation 4100, the circuit was flawless. It had completely perfected its function. Every single tiny error, every little random spike was gone. The evolution was finished.
So, okay, the process worked. The chip evolved itself into a perfect solution. But that just opens up an even bigger, crazier question. How in the world does this thing actually work? What on earth did evolution build inside that chip?
So when the researchers actually looked at the final circuit diagram, they didn't find a neat, tidy design. They found a mess. It was this crazy, tangled web of feedback loops. There was no clear structure, no logical flow that a human would recognize. It looked less like something that was engineered and more like something that had grown.
To even begin to understand this thing, they decided to digitally prune the circuit to try and simplify it. So they traced every possible path from the input to the output, and they snipped away any of the little logic cells that weren't directly on one of those paths. The goal was to basically get rid of the junk and isolate the core essential part of the circuit, or at least that's what they thought they were doing.
And this right here is probably the most shocking discovery of the entire experiment. After they pruned it, they found a handful of logic cells in the final design that had no logical connection to the output whatsoever. They were just floating there. According to digital logic, they shouldn't be doing anything. But, and get this, when the researchers went in and turned off those useless cells, the entire circuit broke. It just stopped working. These totally disconnected cells were somehow absolutely essential.
So what does that even mean? This discovery points to something really profound. The circuit that evolution built, it wasn't playing by the rules of digital design, the rules that we humans came up with. No, it was playing a completely different game.
So what was actually going on? Well, it turns out evolution wasn't just connecting logic gates together. It was actually harnessing the raw, messy physics of the silicon chip itself. Those ghosts in the machine cells, they were probably influencing the other parts of the circuit through subtle things like electromagnetic interference and crosstalk. You know, the very same effects that human engineers spend billions trying to get rid of. Evolution took what we see as a flaw and used it as a feature, creating a solution that was way more compact and efficient than anything a human could have designed.
So the final takeaway here is just, it's incredible. The thing that evolved inside that chip wasn't really a digital computer working with ones and zeros anymore. It was a complex, continuous analog machine that, to use the researchers' own words, was entwined with physics. Think about that. Evolution didn't just write a program for a chip. It sculpted a physical piece of silicon into a brand new kind of machine, one that was perfectly and uniquely tuned for one single task. And that just leaves us with this one last huge question. Remember, this experiment was done decades ago on a tiny little piece of what is now pretty simple technology. So if this is the kind of strange, alien, hyper-efficient solution that evolution could cook up back then, what on earth could it create today?